Okay, so is any questions in general or, whoa. If there's a question about one of the problems, let me know. I can go over it or something. If not, I can kind of find or try to find other problems. Okay, so the table of contents says, okay, so addition of coplanar forces. Now why am I there? Okay, we knew that. Position or directed along the line. And then, okay. So if you're okay, I'll go to section 2.9, and this is, to me, this is interesting because this is the first appearance of the dot product, which I spent most of the time early on starting here. So I'll just do a fill in. His boldface letters indicate a vector, and the not boldface indicate the length of it. So, you know, when I was writing it, I was writing A dotted with B is equal to the magnitude of A, the magnitude of B, and the cosine of the angle between them. A lot of times it's listed like that. So his is no different. It's just you got to get used to a boldface here means it's a vector. Not boldface kind of implies that that's the length of that. A mathematician wouldn't like this notation, but it's okay, I guess, given the fact that maybe he describes all that way. Then you go down to laws of operation. We already talked about if you wanted to find the component of A projected onto B, you would just take a unit vector that goes in the direction of B and dot that with that, and that would give you the projection onto here. So we talked about that. We talked about finding the angle given the fact that we might or we should know the length of these two and their directions, you know, of the vectors. If you knew the vectors, you could find the length. So laws of operation, this is what we talked about earlier, is that if you do that, you have this big long vector dotted with this, then what you'll notice is he's dotted those and put them right here. Then he dotted AX with the BY, put right here, and just lined them all up. As a matter of fact, the only ones that are left are the diagonal ones. The rest of them go away, so I dot I is 1, J dot J is 1, K dot K is 1, so you get that. AX BX plus AY BY plus AZ BZ. So we already did that. We even used this to break down his little three-dimensional thing, which I'm not sure. I could run back that way, but I'm not sure it would be. So here's two unit vectors. You can find the angle between them. And then he goes on and on through this stuff where, I mean, I've gotten myself used to thinking this way exclusively because, and you notice what he does here. This may be why I think this way. You take a vector, you project it on some UA axis, and then he says the other is perpendicular. If it's laying in 2D, I know that's going to have a sign, but it could be that it's in 3D, you know, and so then you may have two components here if it's in 3D. Does that make sense? So it could be maybe maybe this is X, and this is Y, and if you crossed them, Z's coming at you. So it could be this vector A, instead of laying in a plane, maybe it comes out like that. And so here's this vector. Well, you just found its component there on this thing, but it could be that this thing, of course, being perpendicular. Well, okay, he put it like this, but you could put it like that too. I mean, it doesn't really matter. So it could be that this, now in 2D, I always think it's the other, a sine of theta. So I always think that, projecting it onto the axis, the angle between them, the other. That's just the way I think now. I mean, I was trained to think opposite hypotenuse and adjacent earlier in my life, and then I just found this to be more convenient. So I didn't consciously decide to be this way. It just started happening. And so there's some extra videos. Let's see. Instead of doing, there are examples there to look at. Now, do the examples have videos? No, but there will explain. Let's just go to, I think, it's the fundamental problems that have videos, I think. Yeah, so there's some videos there you could look at. And there's some videos. But here, let's just do one. Okay. There, that's a good enough one. 235, 231. Okay, I think I need to shrink it. Okay. How big is that on the board? I guess it's okay. And then I can do this. Or instead of that, you know what's maybe better? Just do that and let MATLAB occupy. Because MATLAB will be clear, so I can fight between the board space and the MATLAB space. So make it go to here. The top of it goes off the board. So here, I can sort of occupy part of this. So he says determine the magnitude of the component acting along the, is it say blue line? I can't, that bar's in the way. Perpendicular, along and perpendicular to this line here, this sort of fake line that he came up with. So, so first of all, there's two ways to do this. But one, the most important way is I have to come to the point where I find the unit vector going from A to D. And then if I want to write this force as a vector, I would multiply times 56 times the unit vector from A to D. Now I got to go after that. Well, how should I do it? So R A to D. So I need to write a vector that goes the entire distance here. Two ways you can do this, okay? He has obviously put his origin here. So I can draw a vector from here to here. And believe it or not, I'm going to have that eventually. So I don't know what's the best thing to do. But I guess I'll just make that vector O to A. And then you just kind of, I guess you could say you're walking the axis. But I'm going to walk them in the way he's kind of drawn them. Okay, so I'm going to walk this one, 3J. So I walk to that one, I got to here. Now I got to go up, which it looks like I go up. Of course, I could have walked this one first, and then that one, and then that one, but it really doesn't matter. I walked out here. Now I've got to walk up 1 meter, and then I got to walk from B to A, 1.5, and that's going backwards. Now, I'm going to walk from the origin to D. ROD. That one's going to be really easy because I don't walk out X or Y. I just go up 2 times K. There's no real reason for me to walk to B or to walk to C. So it could be that maybe there's a question on this related to this picture later that deals with B or C. I don't really know right offhand. So the other way, what you could do is if you're going to walk from A to D, one thing you could do is you could walk straight from A to D. I could run backwards. I'm going to do this 2 ways. I'm going to come up with this vector 2 ways. I'm going to walk this one. I'm going backwards. No, I'm sorry, going forward 1.5i. Then I'm going to walk all the way down here, which is 3, but I'm walking in the negative. And then I'm going to walk up 1. Now that's one way to do it. You could just walk the axis from, and sometimes it may take a little bit of getting used to try to walk those axes or whatever. The other way you could do it is, and this is something that sometimes he writes in the book, this is ROD, this is ROA, this is RAD, and then if you do vector addition, well, if I add this vector to that vector, in other words, RAD plus this vector, my handwriting's not great. I have actually walked the same place as somebody who walks straight from O to D. So since I'm looking for that one, I can basically say RAD is equal to ROD minus ROA. Did I write that right? Okay, so now I've got these two. So I'll just write them out to be complete. Minus 1.5i plus 3j plus 1k minus 2k. So I end up with minus 1.5, and I already see something's wrong here. And then minus, so it'd be minus 1k. So what's wrong here? Let's see. Okay. So ROA, wait a minute. This is AD or OD. So wait, ROA plus ROD. So did I not do that right? Wait. What did I do? What did I do wrong? Say that again?
You said, well, if you're using like a triangle, should have been the hypotenuse should have been RAD. So the ROA plus ROD is equal to RAD.
Well, actually, this doesn't have to be a right triangle. This is just basically, let me make sure. So if I got A and B and C, then B plus C equals the same as A. So if somebody started here and went to here and then here, somebody else could do that. They didn't have to be right triangle, did I? So let's see, what did I do wrong here? Okay, ROA, marching backwards. Make sure I did this part. Marching backwards, marching up or out, and marching 1 up, so going from this spot to here is the same as going from here to here. And this is 2k. So RAD plus ROD, I'm sorry, ROD, ROA, AD. So this vector plus this vector should equal that one. So if I'm looking for that one, I move that one to the other side. This is such a simple thing. So let's see if I'm marching correctly here. I'm starting at A. I go in the positive direction. What am I missing? This is such a simple thing. Isn't that frustrating when you get the simple things? Okay, so I do this. -3, moving that direction, moving up. So I believe this one. I also believe the other one. But they're opposite of each other. A to D, and I'm pretty sure this one's wrong. So this is R, A, D. Okay, let me look at it again. O to A, then A to D. O to A, and A to D. So if I go here, and I go here, I should be the same thing as I go there, right? This is 2. So this one is 2. Start at O, go to here, 2. O to A. Do I go backwards? And I go down this, and I go up that. I think this O to A, I've actually written, wait a minute, A to D, O to D, I wrote the thing backwards. So this is what I wrote backwards. Okay, this is actually R, O to A, and this is actually R, O to D. So that one should have a minus sign on it. This one should have a plus sign. Does that make sense? So I actually just wrote them down backwards. And so that should be plus, that should be plus, and that should be minus. Sometimes things like that happens, you know. So does it make sense what I was doing wrong? So what I was doing is I was taking this one, and instead of putting it where I should have put it, I put it in the wrong place. So I put this one where the other one should have been. So anyway, so now that I've got that, I hope I didn't confuse everyone. I confused myself there for a short period. So now that I've got that, I need to find it in a unit vector sense. So I have a vector that originates at A and runs out to D. And I'm going to write it down again so it'll be closer to me. So when I sit at the monitor, I can type it right here. And that's, you know what, I'll just, 1.5, I'll do a comma, a -3, and then a comma, and then a 1. That'll give it to me in MATLAB form. I can't write that in it, so I'll basically say R, A, D. How about that? So equals to 1.5 -3, -3, and 1. So if you look at it, this is my X component, this is my Y component, that's my Z component. If I want to find the unit vector that goes from A to D, I basically say RA to D over the norm of RA to D. And so I'll do that here, UAD is equal to RAD divided by the norm of RAD. And then I don't know how to say this any more than just writing it down. So I mean, I could write this number as 0.4286 I minus 0.8571J plus 0.2857K. I mean, I don't really know anything more than to do that. If I want to know the force vector, then it's 56, is that right? 56 times UAD. So what I'll do is I'll just call that F, because there's no other F. I don't have to put a subscript on it. And I'll just do that right here. And 56 times UAD. Notice something interesting. They're all integers. Don't expect that. That generally, he's designed these problems to kind of give that. Now, in the homework stuff on the online part, I don't know. It probably won't end up with integers as often. This is a product of design. In other words, if I look at the length or the norm, I never looked at the norm. Let's look at the length of RAD. And it ends up, that vector is 3.5 long. So from here to here is 3.5. If you take 56 and you divide it by 3.5, I bet you're going to get an integer out of it. That's how he designed it. Is that 16 or 15? 16. So in other words, he made it so that he designed it. He picked this number so that when he divided it, he got an integer. So he designed this to give you integers. So anyway, there's that. Okay, so let me go back to the point. Okay, and the point is, the vector, it sits there. Now you got two problems, okay? So you've got this vector. It's hard to, I mean, you see it projected in 3D, but what you've got, let's see if I can, I'm not a great drawer, but I can maybe make a decent attempt since it's put on the board already. So if you broke this down into components, there would be a certain amount going this way. And I don't want to write a number or anything. But then there's another one, and I'm just going to make it up, okay? I'm going to tilt it on purpose to make it look like that. So it looks like it's tilted, right? Okay. But this vector is the perpendicular one. This is the dot one. How about, I could say dot one. How about that? In other words, if I wanted to find this vector's component in this direction, I would find a unit vector, and we're already used to this. We want to find a unit vector going from A to O. Does that make sense? Now, we already had one that went from O to A. So if I want to find one that goes from A to O, guess what? It's just the opposite. 1.5 I minus 3j minus 1k. It goes in the total opposite direction. I found one that went from O to A. Now I want to find one going the other way. So what I'm going to do, I'm going to take this one. I'm going to find the unit normal. Unit normal from from A to O, and I'll get a vector here, and I'll enter it. Maybe I'll take the minute to enter this and find this out. We still have our F, and it's written in it 3 components. So let's do R, A to O. But we already had O to A, right? Did I not have O to A? What did I had AD. I guess I never did. Never mind. R, A to O equals to 1.5 and a minus 3 and then a minus 1. So that's the vector that runs down this imaginary blue line. And I'm going to take this thing and project it on here. Now, it could be that the sunlight, okay, so imagine I'm going to cast the sunlight of a line on this other line. I'm going to have to put the sun in such a way that it's going to project it onto there. So I'm going to have to move it around till that shadow hits that other line. It's like taking this line and this line. I can move them around, but the other way to project onto it is when the shadow of the light source. So it actually, you look at it now, you see a vector like that, but they've got to be such that they're lined up that way. So then what I have, let's say I had a vector here and I projected it onto this. I got another part that's coming out off of that part. And how do you find that? Well, first let's find the one that's projected onto this blue line. And that's easy enough because all you do is now to find this part of the vector, you take the F and you dot it with the UAO. Now, I know this is the magnitude of that and the magnitude of that and the cosine of the angle between them. I don't have the angle between them, but I've got this and I've got that. And that tells me the length of that vector down that blue line. And so I got to do that now. So I think I have RAO and I have F, so I can do dot of RAO with F, and it gets me a number. Wow, but that's not what I'm supposed to. Where's my U vector? Did I not find my U vector first? Okay, mistake here. It's supposed to be dotted with the U. Okay. UAO equal to RAO divided by the norm of RAO. Okay. There's my unit vector, okay? So I need to dot it with this unit vector. I was dotting it with the R. That's not going to give you the right answer. Dot it with the unit vector. Now, dot F with UAO. Gosh, I can't even read that there. I can read it better here. 46. So if I were to look at it, F dotted with UAO equal 46.8571. Now, if I wanted to know the one component of the vector that was perpendicular, he draws this line as being perpendicular. If the magnitude that's perpendicular to the UL, what would you do? How would you do that? Okay, you're getting on the right track. Okay, so what you're saying, okay, let's just say, okay, I know I have to have a sunlight that's going to cast it into there. So depending on where I'm going to look, I'm going to see one plane that's going to look like this. I don't know the angle between it, but let's just say this is 46.8571. And then I got another one up here, and here's your F. So this is 56. Okay, so what you've got is you got a vector that's this. You got this one that's perpendicular. Oh, I'm sorry, I didn't finish that. Now what is it? You're on the right track, but it actually ends up being whatever that magnitude or number is squared plus that number squared has to equal that number squared because it's a triangle. So in fact, what you do, 56 squared minus 46.85 squared, and I'll explain this again in a second. And that should be that. That should be that number.
I already have a question.
Okay.
So if it's not a right triangle.
Okay, by definition, it'll always be a right triangle. So, and here's the thing. The reason being is because, okay, so think about it like this. Okay, it may take me a minute to kind of explain this. So I have a vector out here in space, and I found it, but somewhere around there I can break it into two components. One of them laid on that line, right? And so you can't just arbitrarily do it. So that this vector and another vector line up so that it's pointing in the right direction. They got to be 90 degrees. So it makes a triangle but it doesn't make it in this plane. It kind of makes it so somebody whose head looks down and sees up at, oh, I see the triangle. But in fact, this is the case. Does that make sense? And so that's kind of why he uses this symbol here. He always says perpendicular to the other one. So and that may be why my mentality went this way. It's like a dot product, cosine, and the other one. And so most of the time I think, oh, that's got to be the sine. But I don't have the angle. Nobody has the angle here. I mean, we could find the angle, but who cares? Why would we want to find the angle? I can just do that and get the other one. So this is probably why my mind has moved in that direction to the point where there's a cosine and then the other one. And so I don't know that, yeah.
So your projection is going to form around triangles, like you were saying.
Yeah,
right.
yeah.
Right. Okay, that makes sense.
Yeah. And so that, I don't know, just over the years this has happened to me, and it makes it easier for me to do things like that, different things. So yeah, it always, the sun will cast down, it'll hit the ground. I mean, you think about it, no matter what you do, if you had to if I turn on the lights, they're going to come from all different directions, but if you just had one coming straight down, and I just put a vector out there, like I stand in the corner and I point to right here, and then I project straight down, then actually, if I look at the line of the projection, it'll make a perfect triangle. The line coming off here, the shadow on the ground, and straight up. So no matter where I go, that one coming straight down is going to make that 90-degree right from this line down. So it always makes that 90-degree, the projection does. So in the book, which, well, I guess I do have the book right here. So in the book somewhere, yeah, because I'm looking at the book. Let's see. Okay, give it a second. He has it, so he goes down here. Let me see if I can find out where he may do it here. He may not do it here, but okay. Important points. Oh, and then it's done. Okay, well. Oh well. Oh, I was on fundamental problems? I was on fundamental problems, wasn't I? Yeah, I was on the last one. So maybe in the problems is where he does it. Let me see where one of the problems. Okay, well, well, here he's actually using the word projection. So he's kind of using that word here. So this is kind of, okay, so this is a weird one, but in fact, it probably is appropriate to talk about. He took this 100 Newton one and projected it on that V, and he did so, it made this. So it made that 90 degrees. So it always makes the right triangle. So you're stuck here, and if you figured out one of them, if in case he wanted to know this one, you would take this one squared, whatever that length is squared, whatever this length is squared, and then you add them, and it would be this one squared. So whenever those things happen, they're projections. So he's done something weird here. He projected it over here, and then he projected it over here. That's bizarre, if you think about it, because how does this one relate to that one? Well, it really doesn't. But it is the projection of this one on this axis and the projection of that one on that axis. Does it really make sense why he's doing that? Not really, not at this point, because neither one's going down a coordinate axis. So
is the projection just like the amount of work done by on that direction?
okay, so now so when you get into dynamics, actually, the answer to that question, the work done is basically a force dotted with the direction the object moved, right? So if I push straight down, it doesn't move, I didn't do anything. But if I push at an angle, and of course this is dynamics, so that's not this, but in fact, you know, the F dot X, the distance it moved, yes, in fact, you take the component of my force going this direction that's making the table move like that, and then the distance it moves. So it is a dot product, and the dot product is, in fact, the work, you know, that takes place. So they are related, and, you know, the difference is and you're thinking along the same lines, or the right lines. Now, that's dynamics, but since you brought that up, most everybody had physics to get here. So so in fact, yes, that is the case, and I'm probably not supposed to do it legally, but here, let me get this MATLAB back up. But in fact, if you put a force on something, say F is, let's make it go the other way, because then I can, so put a force like this on some sort of object, like a box. F is equal to 3I plus 2J. And then the box moved this way, X, or say the distance, or the, say delta vector, it moved was like 3I. Then essentially, the F dotted with the delta is that times that, or 9, and there is no I, there is no J. So it turns out only that component of the force that pulled in the direction of the object's movement contributed to its work. And so, yeah, in fact, the dot product associated with work is the same thing. We're doing it in a slightly different context because we're actually wanting to find unit vectors and then dot them with that, because then we can find the component in that particular direction. But the mathematics between these two is actually the exact same thing. It's just we're answering two different questions. The question here is, what's the force being pulled along here? And then what's the other component's value? And so it's a little bit weird. However, it's not that weird, because let's say I'm taking the door, for example, and then I pull like this up on it. Then whatever I'm pulling, only component that's moving the door is the one that's going this direction. So I'm pulling this way. I'm not doing anything. If I pull straight here, okay, so why is that important? If you look at the component going up the axis of the hinges and you dot that, what you're going to see is the force I have is pulling this way on the door, up on the hinges of the door. But if I don't pull in this way, the door doesn't move. So you're interested in dotting this vector with that vector, and you find nothing. So you find the door doesn't move. So sometimes there's a line and then another line. So I drew a line up the thing, and then I drew a line straight off of the surface, created kind of my own sort of vector. So maybe I'm doing X, Y, and Z. Then I have a vector coming out of the door, and then I have a vector going up the door. Okay, yeah, I pull like that. I get one going up the door, this way, okay, but I don't get one this way. So if I dot this vector with that one, guess what? They're 90 degrees apart, or 90 degrees from each other, and the dot product gives you nothing. So this is where, you know, you might have some interesting things. You might have some sort of mechanism that's doing like that, and you're pulling on it. Well, wait a minute. You don't want to pull it this way to make it move. You got to pull it that way. But I have a rope over there that's pulling, and, you know, it's kind of making it do things like that.
So how come F dot the unit vector of AD isn't 0?
Okay, unit vector.
You have it in boxes. F times the unit vector of AD.
This one?
Yeah, why is it at 0? You're saying it's perpendicular?
Okay, so here's the thing with it is, okay, all right, so on this one, I calculated that, okay, but I did not know, I just was given that, okay, I found that one. That was the, what was it, 46? Okay, so I went through the mechanism to find that one. So I found this. From the mathematics, I found that it's 24I minus 48J plus 16K. So I found that by running up this line and then finding the unit vector along that line and then multiplying it times 56. Yeah, 56. It's kind of hidden right there. So I found that. Okay, the other thing is he told me that I want to find this blue line. So this is A to O. So I found that vector. And then it turned out I found the UAO from that, which was just. Now, here's the deal. I don't know the angle between UAO and F. So think about that for a minute. If I'm looking at this and I say, what is the angle between this line and this line? I don't really know. I don't know what that is. But I do know F dotted UAO is equal to the magnitude of F, which is 56, is the magnitude of UAO, which is 1 times the cosine of whatever that is. So theta between the two. I don't know here, F and U. How about that? So I don't know what that angle is. But I do know I dot these two funny looking vectors and I get 46. What did I get? 46. So I end up on this side, I end up with 46.857, right? Equals to 56 cosine of theta between those angles. So actually, I could do this, 46.857, 556, and cosine inverse. That will give me the angle between those two. But if, in fact, it was 90, then that wouldn't be very good because, I mean, if it's 90, there wouldn't be anything. But it turns out that it's not. If I wanted to find that, arc cosine degree of 46.857 divided by 56, turns out that angle is around 33 degrees. So if you look at it, the angle between these two is around 33 degrees. Now, okay, so you got to think about this for a minute. And again, it's hard to draw, and I think I goofed it up there a little bit. So you got 33 degrees, and say you got that one. So this is 46. Turns out that's the case. Wait, 46.857. This is 56, and that's something. So it turns out it's kind of tilted maybe a little bit. If you really want to get berserky, can you tell me what is this vector? What is that vector? What are the components of that vector? Okay, let's think about this. Okay, we found out this is 46, right? Okay, so bear with me. This is 46. That's the length right there. So I want to find the force vector that goes from A to O. I contend, now let's think about this, 46.7 times the unit vector, which goes from A to O. Is that true? Think about that. Give yourself a second to think about that. So I've said this vector runs down that. We're about to go find the actual vector here, this vector that he calls perpendicular. I'm going to find it in components. Okay, he lists it like this. I'm going to find this in the I and the J and the K. This is something he doesn't do in the textbook, but do you buy into this? Does that make sense? If I had a vector that went down that, and that says 46, if I multiply it times AO, if I found that, guess what? I already have it. Okay, so let's find that. FP for perpendicular. Okay, 46.857, is that what I wrote? 8571. 8571 times UAO. There's my vector. So it looks bizarre, doesn't it? So if I had two vectors and I'm adding them, I take this vector and I add that vector to it, I get this one, right? So if I want this one, isn't this one equal to the original vector minus this vector perpendicular? I mean, not perpendicular, but this vector along AO. Here, let me write that in red so it makes better sense. So here, I want to find this perpendicular one is F minus, this F minus the F along AO, which is this one. Okay, so let's, now this may be a lot, and I wouldn't do this except that we have a lecture here that we can record. F minus FAO, no wait, did I call it FAO? No, I called it FP, perpendicular. Which actually, okay, so now that I have that one, what do you think the magnitude of that one is? Is that the same thing I got? Did I ever find that? I don't think I ever found that one, did I? Did I find that one? Okay, so what's this squared times that squared? 30, 46. So I never really found, I didn't ever go in and find this. The 56 minus 46.8571 squared was that. Is that equal to that? And that's a good question. So I never found that. I should have. 56. Oh, no. Well, it's a good thing I'm still recording. I'll just keep going. Y'all can go ahead. And I'm just on a roll. I'll just keep going. You know, I started lecturing statics in fluid. So let me do it. 56 minus 46. 46.857. And then square it, and what is it equal? Guess what? 30.666366. So it worked. So I'll come back to this next time. Since we have a lecture, I can come back to it. I can project the lecture on the board and then answer questions about the... Sorry, I didn't mean to run over, but... Especially if you got somewhere else to go, and I just got to notice I'm supposed to be in fluid, so. You too.